Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics in our third video about collisions. Today we will start exploring the center of mass frame for collisions. First of all, we will understand what the position of the objects are in the center of mass frame. After that, we will see what the relative velocity is in the center of mass frame, and then we will apply some of our conclusions we got in the last video to our center of mass frame. So, let's start! Great, let's try to find the center of mass of these objects, and after that the position in that center of mass frame. Our center of mass is defined to be at this place, R1 M1 plus R2 M2 divided by M1 plus M2. In any case, it's always going to be in between our masses, so we'll draw it right around here, the ZM, center of mass. Also, we would like to draw the vector that goes from mass 2 to mass 1, R2, 1. And we see that this vector R2 plus R21 gives us R1. Therefore, 2 plus R21 equals R1. So, R21 equals R1 minus R2. Once we have this quantity, it will be very useful to express everything in our center of mass frame in terms of this quantity, as it doesn't depend on the frame in which we are working. Now we would like to find what the positions in the center of mass frame are. So we would like to find a vector right around here that is going to be called R1 prime. And R1 prime, it's going to be equal to R1 minus R. As you can see from this vector triangle, R plus R1 prime equals R1, therefore R1 prime is R1 minus R. So R1 prime minus, and I'm going to substitute directly this R1, sorry, this is not a prime. Knowing this, we can combine them and we get now we see that some cancellations start to appear, as we can cancel R1M1 with this minus R1M1. And also, we can take the common product of M2 out of the equation, so that we get R1 plus, sorry, this would be a minus. So minus R2, all of it times M2 divided by M1 plus M2. Now we're going to define a special quantity that is called the reduced mass, and it's pretty useful in doing simplifications in this type of situations in which we have two objects. So this reduced mass is going to be defined this way. If we operate this quantity, we find it to be equal to M1 M2 divided by M1 plus M2. And we see that we have a pretty similar situation here. We're just missing an M1 factor. So we're going to express this quantity in terms of our R21 and our reduced mass over there and M1. So we get mu over M1 times R21. Now we can express R2 prime by swapping 1s and 2s, as it's a symmetric situation for both of them, and we will get the same mu as we can swap them without any problem. We will get an M2 right down over there, and be careful that R21 is the negative of R12. Therefore, we have to add a minus sign over here, and we have now the R21. And these are the positions in the center of mass frame. Great, now we'll explore relative velocity. We're going to do some changes to the notation we had earlier. We're going to call the vector that goes from 2 to 1, we're going to call it R12, just because it's more convenient and it's easier to memorize that it's R1 minus R2. And this is also the standard notation, that going from 2 to 1. Because when you are doing forces and things, it's the force that 1 exerts on 2, and it's going to be of this form. So it's just a small thing of notation. And also, relative velocity is now going to be, instead of B-rel, it's going to be B12, which is B1 minus B2. So, same definitions, but just some tiny changes to the notation. Now that we have this, we are going to demonstrate that the relative velocity is the same in all reference frames. So to do so, we will show that R1 equals R plus R1 prime. And we know similarly that R2 equals R plus R2 prime. Now that we know this, we may combine these two objects. So we get R1 minus R2 equals R minus R cancels, and we get R1 prime minus R2 prime. And we already know that this quantity R12 is the same both in the CM center of mass frame or any lab frame or any frame we want, in all frames. But now here's the important step. We're going to differentiate this quantity, and what we're going to get is B1 over here minus a B2 equals to a B1 prime, differentiating with respect to time, to be clear, and a B2 prime. And in this side, we have our B12, and on this side, we have our B12 prime. Therefore, we conclude that our relative velocity it's the same in all reference frames, the same as with our relative position, as it only depends on the position of the masses. It doesn't depend on your reference frame nor anything similar. And this is a very useful fact. Right, from last time you have alright. Last time we derived a momentum kinetic equation relations about the relative velocity, and that said that the initial relative velocity v12 initial equals the opposite of the final relative velocity. Knowing this, we will apply it to our reference frame, the center of mass reference frame. Remember that R1 prime equals mu over m R12. And now we can differentiate both sides of this equation to find that B1 prime equals mu over m B12, which we know to be the same in all reference frames. So it's going to follow this relationship. We also know that R2 prime equals mu over m2, this would be m1, times R12 and a minus sign right over there. If we differentiate both sides of this equation, once again, we're going to get that B2 prime is going to be equal to minus mu m2 B12. Now, this is going to be right, both when we are going in the initial, when both objects are getting closer together, and on the final, when both objects are going away. And what we can deduce from this relationship is that as the B12 only changes sign from one to the other, what we're going to get is a change of sign in these velocities. In that way, B1 initial prime is going to be equal to minus B1 final prime. And B prime to initial is going to be also the opposite to the final one. Because what happens between the initial and the final is a change of sign, as we said, and these two are proportional to the relative velocity. Therefore, if there is a change of sign, there is going to be a change of sign in them. And this is a very important relationship that lets us know very well what happens in an elastic collision in the center of mass frame. Each object just returns with exact same velocity, but in the other direction. That is all for today. I hope you understood everything correctly and also that it helped you get a sense of how these collisions work by exploring them from a different frame, by exploring them from a different reference frame, the center of mass frame. In the following videos, we will conclude with this collision series and we will start with another topics about classical mechanics. I hope you understood everything, but if there is any doubts left, you may ask them in the comment section and I try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the following videos. See you another day with more Physicawesome!